the area problem is the other major problem that we need to talk about that really started the whole idea of calculus. Um, and here's the basic idea behind this. Suppose I have, again, some curve. And let's just say that it's that same curve we dealt with earlier. And I'm going to make this y equals negative 16x squared plus 100x. So this is x and this is y. Before, this was a position function, but right now, quite honestly, it doesn't matter what it represents. What I'm trying to do is I'm trying to figure out how much area is under this curve. Now, we don't know how to do that. As a matter of fact, we can't do that with algebra. With calculus, we can, but there's no way to do this with algebra. If I gave you a rectangle and I told you that this has a height of h and a width of w, well, we know that this area is going to be height times width. So long as I give you the height and the width, then you could figure out what the area is of this particular rectangle. Now, we have other forms that we know, such as a triangle. If we have a triangle, and let's say this is B for the base, and this here represents H for the height. Well, we know that the area for a triangle is going to be 1/2 height times base. Certain geometric figures we know. What about this curve? We don't know. But suppose I were to take and make rectangles out of this. I'm going to use the left side of the rectangle. I'm going to make this as high as the curve. So this next rectangle could be as high as this curve. And the next rectangle on the left side is going to be as high as the curve. And so forth. If I do this, then by adding up all the areas of these rectangles, I can actually get an idea of what the area is under the curve. Now, there's obviously some immediate problems. See here, I skip all this. This is all underestimation. Over here is overestimation. So one thought may be no big deal because these will cancel each other out. Well, maybe, maybe not, depending on the geometric shape. But I know this height because I know the value of x, say right here. So I know that this is just f of x. And I know the distance between these 2 points here. Then I can find the area of this one curve. And I can add them all up. So if I take the distance between these 2 points right here, and I make all these distances the same for each of these rectangles, the base of the rectangle is all the same. If I take this and make this really small, whoops, small with an S, there we go. So these rectangles are going to get very, very, very narrow. Then I will get a better and better estimation of what this area is under the curve. So I'm going to go ahead and jump to Maple here. And I need to do with student and calculus 1. And what that's going to do is it's going to give me a bunch of commands here that I have available to me. And one of the things I can do is to suppress all those commands. If I put a colon here, then it won't fill up my screen with all that stuff. So what I want is I want a Riemann sum. Now, don't worry about the name of this. We will talk a bunch about Riemann sums later. And I want my function, so negative 16x squared plus 100x. And I will let x go from 0 to 6.25. And method equals left. This is going to give me these boxes where the left side of the box is going to line up with the curve. And I'm going to set it to an animation, because animation is kind of cool. Okay, so here's my box. In my partition, this is 10. That's telling me I have 10 different boxes. And you can see the left side of the box, the height of the box is based on the left side matching the curve. And this stuff here, it uses some lingo that we don't know yet, but that's okay. The bottom line here is it's adding up all these 10 boxes, and it's saying the area is 644.53-ish. based on 10 different boxes. Now, when I click on it, the animation comes up, and I'm just going to scrub through this animation real slow. First thing, I'm going to jump to the next frame. There we go. See, now I have 20 partitions, which means I have 20 different boxes. And see, the area just changed, 649.41. I'm going to increase the number of boxes a little bit more. See, now I'm at 40 partition. It went from 641 to 650.63. And you can see these boxes are getting narrower and narrower and narrower. So my over and underestimation, see over here I'm still underestimating a little bit. Over here I'm still overestimating a little bit. Those errors are getting smaller and smaller and smaller. So if I keep going, I mean, based on the animation, all of a sudden it's just going to look solid. And we're at 320 partitions. Now, let's just suppose that rather than 320 partitions, I have a way to get an infinite number of partitions. That means the width of each partition would then become, or approach, 0. So my approximation would no longer be an approximation. It would actually give me the actual area under the curve. So again, here, this area I can see is underestimating. That's an area, or that's an error. This area over here is overestimating. That's an error. And again, as I increase the number of partitions, so each of these get smaller and smaller and smaller, what I get is a better and better approximation, because the errors are getting smaller and smaller and smaller. Again, this idea is based, once again, on a limit. What happens is as I let those two x's get closer and closer and closer together, in the limit, those two values of x become 0, or they approach 0, so I end up with an infinite number of boxes in there. So in a nutshell, that's the idea behind the area problem. And this whole idea of finding a limit, letting these two values of x, this one and this one, get infinitely close to each other. That means all of these are getting infinitely close to each other. That whole idea is the idea of a limit, and that's what calculus is actually based on.